Hello and welcome back. Today we are talking about section 2.6, implicit differentiation and related rates. In the first video here we're going to try to talk about implicit differentiation and using it to find slopes and rates of change. So a quick reminder first, the chain rule is going to make a lot of appearance throughout this section, and there's a perfectly valid argument that basically everything we do in 2.6 is really just a fancy version of chain rule. But it's such a challenging topic in a lot of ways and an important topic that it makes sense for us to spend more time on it, approaching from different angles. So the reminder is that if you have some function of a variable, but that variable itself is more complicated, it also depends on something else. So we have f of u, but u itself depends on x. If I'd like to find the derivative of f with respect to x, we first get to basically pretend like our original expression with u's in it. We can take the derivative just like that, and then chain rule makes us tack on the derivative of this other function. So we're doing composition with f and g, and the chain rule tells us that the derivative of this composite thing is the derivative of the outside, that is the f of u, times the derivative of the inside, that's the g of x. So implicit differentiation, there's two pieces to this new phrase we're defining. The differentiation piece is something that we're used to. Differentiation just means to take the derivative of something. So that much is familiar, the process of computing derivatives of the terms. And in this case, what's maybe partially new is that we're working with two sides of an equation. And the reason that's the case is because of this implicit nature. So usually we do this when solving for, we could just say solving for y, but any dependent variable is really difficult, or maybe it's even impossible to do algebraically. So we have some equation with x's and y's all kind of commingled, and it's very challenging to write it as y equals x stuff. It turns out that even in that scenario, although it doesn't seem plausible, we can't get y by itself, but we actually can isolate dy dx. We can find the derivative of this variable. So let's try to justify this. So here's our expression. If in case we're curious, the graph is an ellipse. And we're going to try to approach this in two different ways. The first way, we're going to do this in a more standard kind of approach. We'll get y by itself. So we'll have y equals stuff with x's, and then we'll just take the derivative of the stuff on the right side. That's not implicit differentiation. You could call that explicit differentiation if you wanted to. But then we'll compute this by leaving all of these terms alone. Leaving them exactly where they are and differentiating every term in this equation, and then solving for the dy dx term. And then finally, we should show that these two results give us the same thing. Okay, so strategy one, we're going to get y by itself first. So here's our equation for the ellipse. We're going to subtract 2x squared to the other side, and then square root. And as usual, whenever we introduce a new square root to our equation, we're going to get two possibilities, either the positive or the negative version of this answer. So once we've got y by itself, we're going to take the derivative. So dy dx, this just means the derivative of y. So another way of writing this in common expression would be y prime. The prime notation starts to fail us right when we hit chain rule. So it's been a little bit iffy whether writing prime of something really gives us all the information. So this notation, this Leibniz notation, is more cumbersome, but it also serves a purpose. It reminds us that the input variable is x in this case, and it turns out that matters a lot with chain rule because sometimes we don't know if it's x or it's t or what have you. Okay, at any rate, the right side says take the derivative of the y stuff. So this was just our answer from the last slide. We can ignore the plus or minus since that's just part of this constant. We can bring 1/2 down from the exponent since the square root is really a 1/2 power, and then subtract 1 from our exponent. And then, as usual, we've got this inside piece to pay attention to. But chain rule lets us tackle this without too much trouble. It says, look, you want the derivative of this complicated expression under the radical, that's fine. Pretend like all the stuff in blue is just x for the short run. But then you have to multiply by the derivative of the inside. So this piece right here is the derivative of 8 minus 2x squared. So putting these terms together, we get kind of a cute expression here. And this used to be plus or minus. Now it looks like minus plus. This is one of those mathematician kind of tricks that basically just says, look, if you take a negative and you multiply by plus or minus, that's going to create the opposite sign that you had before. So where this expression was positive, the fraction down below would be negative, and vice versa. So really we can just still think, all right, this whole expression has the potential to be either positive or negative. So part B, we're going to try this same derivative thing, but with this new strategy. The first thing we do is leave everything alone. So the first strategy, there's our equation originally, is taking the derivative of all these terms. So we're not even moving anything before this happens. So this is just expressing that we can break up derivatives over addition, so nothing super fancy there. And derivative of 2x squared is pretty familiar. We just get 4x because x is our input variable, nothing fancy happens. The more exciting piece is with this chunk right here. In our next slide, we'll talk a little bit more about it. But what happens here that's obvious is that we look at 2y and we think, sure, regardless of how complicated this is, derivative of something squared is going to be 2 times that thing. But it's the agreement of, or lack thereof, agreement in variables that's what really matters in this case. We're supposed to take this derivative with respect to x. This is y. So even a cursory glance at this would show that these variables are different. But here's the thing. We know that y depends on x somehow. The original equation we gave us, the stuff that's underlined in red here, shows us that x and y are connected. So really when I see y, I should think something complicated that involves x's. So this is some big parentheses thing all getting squared. Well, the derivative of something with x's in it squared initially looks like 2 times that stuff. Chain rule makes us tack on the derivative of the inside. The inside, I'm air quoting here, which you can't see, is just y. So what chain rule really wants us to tack on is the derivative of y. This is kind of an awkward situation because this whole problem, this whole example started with the goal of finding out what dy dx is equal to. So I have no idea what this is. But it turns out that chain rule is better than your local bank or credit union or anything. It'll take IOUs. It'll say, look, you can tell it. I know this is where the derivative is supposed to go. I just don't know what it is yet. So here's a little placeholder that represents the derivative of y. Okay, so this is just accentuating this process in writing. So that last piece that we just discussed is where most of the challenge comes in. So every term gets differentiated with x in mind. So when we run into y, we really have to pay close attention to this. So y itself depends on x, so chain rule is what kicks in. We have to think of y as something with x's in it. Okay, so we're not quite done yet. We do have this is just reiterating our expression from before. The derivative of 8 on the right side was just 0, so that was kind of anticlimactic. But the goal at this point, phase 2, is to solve for dy dx. So actually all of the calculus is done at this point. What we're really down to is figuring out how to get this by itself. But we're good at this. We do this in algebra all the time. We can subtract 4 from both sides, 4x from both sides to get 4x on the right, and then we can divide everything by 2y. So this is actually our final answer as far as implicit differentiation is concerned. Now, if you recall, part B had this follow-up. We were supposed to look at this and say answers in part A and part B should be the same. Well, they don't look it. Here's our answer in part A. This is minus plus this fraction. And then in part B, our answer for the same thing looks like that. These actually look kind of different from one another. But with a little bit of adjustment to part B, we can make them look the same. So for instance, we have a factor of 2 in common top and bottom. So we could just have 2x on top. That starts to make this look like the fraction up here. But even better, we can replace y with the expression we know it to be. Remember back in part A, we actually solved this for y. So y really was all of that stuff, plus or minus square root of 8 minus 2x squared. So with these factors canceled out, and we're down to just 2, actually these things really do look the same. We have 2x and 2x. We've got 8 minus 2x squared square rooted. And the only difference is this plus minus minus plus situation, but if we use that same convention that we had before, this weird, like, I've got a negative here times, or really divided by, doesn't matter, signs change either way, then these two things together make this minus plus situation. So actually the expressions from part A and part B really are the same as one another. There's lots more to do with implicit differentiation, but this is a first glance. We'll do more in class, and we'll be back with another video to talk about related rates. See you then.